A warm welcome to one and all gathered here virtually. Let me start with the quote: don't downgrade your dream just to fit your reality. Upgrade your conviction to match your destiny. Hereby, welcoming you all for the IEEE Madras section sponsored Faculty Development Program on Smart Grid Trends and Future Perspective, organized by Department of Electrical and Electronics Engineering of King's College of Engineering. We are having webinar for 2 consecutive days in 4 sessions taken by 4 different resource persons. Now, I would like to call upon Dr. M. Meenalochani, Assistant Professor Triple E, to start with a pleasant welcome address.
Good morning to you all. Thank you for joining us for IEEE sponsored today's FDP on Smart Grid Trends and Future Perspective. I would like to extend my warm welcome to our Secretary Sir, Dr. Rajendran, for joining this session. Welcome you, sir. My heartiest welcome to our Principal, Dr. J. Arputha Vijaya Selvi, ma'am, for joining this inaugural session. Welcome you, ma'am. I consider it a great honor to welcome Dr.N.Kumarappan, Professor, Department of IEEE, Annamalai University, and Chair, IEEE Madras section for this inaugural session. Welcome you, sir. It's my pleasure to welcome Dr. M.Venkatakirthiga, Associate Professor, Department of IEEE, NIT Trichy, for joining this session. Welcome you, ma'am. It gives me immense pleasure to welcome Dr. A. Albert Martin Ruben, HOD, Department of IEEE, to this inaugural session. Welcome you, sir. My warm welcome to the faculty of King's College of Engineering and external faculty from various colleges for joining this FDP. Welcome you all.
Thank you, ma'am, for your welcome. Next, I would like to call upon our principal, Dr. J. Arputha Vijay Selvi, ma'am, to deliver the presidential address.
Chair, IEEE Madras section, Professor IEEE, Annamalai University. Beloved Madam Dr.M.Venkatakirthiga, Associate Professor IEEE NIT Trichy. Dr. A. Albert Martin Ruben, Convener of this FDP. Dr. M.Meenalochani, Coordinator. Faculty, staff of IEEE Department. Delegates from various institutions. HODs, faculty and staff of King's College of Engineering. A very good morning to all. I am extremely happy to preside over the inaugural session of IEEE Madras section sponsored FDP on Smart Grid Trends and Future Perspective, organized by Department of IEEE, King's College of Engineering, for managing the grids of the future. Smart grids represent a new era in the electrical sector as we go from static one-way management to dynamic two-way management. This improves the efficiency and energy savings. The National Smart Grid Mission was approved by the Indian Ministry of Power on 27 March 2015. Currently, it has allocated 14 smart grid pilot projects across India. Under the Smart City Mission, all electricity supply in smart cities will be through smart grids. This technology would be a step forward to solve the energy strain that our country is facing and preparing for the renewable energy and efficient distribution systems. I hope this FDP will provide an insight to smart grid, the technologies used in smart grid, and its recent developments. I appreciate the organizing team for their marvelous efforts towards organizing this FDP. My sincere gratitude to Dr.N.Kumarappan sir, Chair, IEEE, for being with us today. My sincere thanks to Dr. M.Venkatakirthiga, Associate Professor, IEEE, NIT Tiruchirappalli, for giving consent to act as resource person. Once again, I congratulate the organizers and wish the team all the best. Thank you all.
Thank you, ma'am, for your presidential address. Next, I would like to call upon Dr. N. Kumarappan, Chairperson, IEEE Madras section, to give an inaugural address.
Our respected Principal, Dr. Arputha Selvi, and beloved Associate Professor Dr. Venkatakirthiga, organizers of this event, Dr.M.Meenalochani, and dear participant of this FDP program. Good morning to one and all. This is one of the IEEE Madras section sponsored FDP, going to be held under the banner of King's College of Engineering, Suram branch. But this is one of the essential and important topic at present. And different kind of grids are emerging now. These are all essential to meet out our future energies. Therefore, once we list a different kind of a grid, there is initially a fight between the scientists between Tesla and Edison. Finally, Tesla won. Initially, they formed the AC grid. Edison insisted about a DC grid. The reason is producing power, transmitting power, and even consuming power, all by AC. Now, what happened? The present scenario, the grid is entirely changed. Now it becomes a AC-DC grid. And not only that, the AC-DC grid, according to the AC-DC grid, we are in a position to solve a different kind of problem, the avenue of research improve further. And beyond that, there is another grid is called microgrid. Once we talk about a micro, the word is naturally belongs to electronics. Micro dominates in electronics. The reason is we see the 10 to the power minus 6 or 10 to the power minus 3 or now approaching to the nano 10 to the power minus 9. All kind of amperes we realize because of electronics. Therefore, that make us to consumption the power as very less. That's why compared to electrical electronics dominates as well as popular. But even equally, we use the word micro in electrically. That's what do you mean by that? But now we produce a power. We use megawatt, but even we can produce a power in terms of kilowatt. That makes us to form a microgrid. Microgrid can be connected to the main grid. Otherwise, it is to be acted as in an isolated manner. Both it is possible. Next kind of a grid is called as a smart grid. The smart grid, you really want to form a smart grid. According to the 2003 Electricity Act, it is must implement the power system restructuring. Almost all the states' electricity boards are implemented. Tamil Nadu it is unbundled as TANGEDCO and DISCO. But in Andhra, unbundled as three kind of different ways: TRANSCO, GENCO, and DISCO. Therefore, even now, we are in a position to beat the power bill based on this 2003 Act. Therefore, we are now already forming the Indian market. Through that, we can even form a power exchange. I got the chance of visiting Baltimore, USA, the power exchange. It is very interesting. Each and every time the bit of the power is going on changing. Therefore, that is the restructuring. Together with the restructuring, now we are in a position to implement a smart grid. What do you mean by smart grid? We require a bidirectional kind of a flow. At present, it is not that. Therefore, it is to be re-engineering to be done to make the whole thing to be bidirectional. Present system is only based on one direction. Once you are done, not only that, parallelly the communication line also required that also to be in bidirectional. Where there may be excess power, you can easily get it. Therefore, that is exactly called as a smart grid. Now, smart grid is only in the initial stage in India. Power systems restructuring already implemented. The next level of grid is called super grid. What do you mean by that? You get an excess power from other countries. You can get that power also. That is one continent to other continent, one country to the other country. That way you can easily get the power. That is called as a super grid. That is also a very difficult task because even when we visit other country, we always go with an adapter, that too as a universal adapter. Therefore, even the voltage differ from one country to other country. To make it that as a smart super grid, we require a common kind of voltage. Therefore, achieving such a kind of grid, different kind of a challenges are there in front of us. Once we meet out, even we can approach a super grid. About this, according to this kind of a different kind of a grid development, what is the topic you selected today for this FDP is a wonderful and essential topic at present. Therefore, once the teachers get trained, they can easily mold the students. In the student's perspective, what is the way they look at the teacher? Once I say that way, based on that, we make a conclusion. What is actually the perspective of students? What is the way they look at the teachers? குழந்தைகள் என்றால் உச்சி முகரலாம், நண்பர்கள் என்றால் ஆலிங்கனம் செய்யலாம், உறவுகள் என்றால் அடித்து கூட பேசலாம், அதிகாரம் என்றால் கைகள் இணைக்கலாம். ஆனால் ஆசிரியர்கள், பேராசிரியர்கள் என்றால் கைகள் மட்டுமே கூப்பப்பட வேண்டும். அந்த நிலையில் நம் மாணவர்கள் நம்மை வைத்திருக்கிறார். அந்த நிலையை தொடர்ந்து தக்க வைக்க வேண்டும் என்றால் இந்த FDP essential. Thank you for the opportunity.
Thank you, sir, for your wonderful words. Now we are entering into today's forenoon session handled by Dr.M.Venkatakirthiga, Associate Professor, EEE, NIT Trichy. I am extremely happy to introduce our resource person for the forenoon session, Ms. Dr. M. Venkatakirthiga, to the audience. She obtained her graduation in Electrical and Electronics Engineering from Annamalai Mahalingam College of Engineering, Kovilveni. She obtained her M.Tech in Power Systems from National Institute of Technology, Tiruchirappalli. She received her doctorate from NIT Tiruchirappalli in the area of distributed generation and microgrids. At present, she is working as an associate professor in Electrical and Electronic Engineering Department in NIT Tiruchirappalli. She is having about 18 years of teaching experience. Her area of interest includes distributed generation, microgrids, power systems, and electrical machines. She has guided around 90 PG projects and 26 UG projects. She has published around 20 papers in essay journals. She has undergone study tour under the guidance of Dr. Lalit Goyal at Nanyang Technological University from 29th June to 9th July 2013. At present, she is guiding 5 PhD scholars and 1 MS student under her supervision. 2 PhD scholars and 1 MS student received their degree under her guidance. She is a reviewer of various reputed journals including Electrical Power Concept, Components and Systems, Taylor and Francis Journal since 2012. IEEE Transaction on Smart Grid since June 2013. International Journal of Emerging Electric Power Systems since November 2013. International Journal of Electrical Conversion and Management, LC1 since 2013. IEEE System Journal since 2018. And also she held various positions like Associate Dean in Students Welfare for Girls from November 2015 to November 2017. And also as Faculty in Charge in Guidance and Counseling Cell from November 2015 to November 2017. And also as Associate Dean Alumni Affair from December 2017 to December 2018. We welcome you, ma'am. Now I'm going to hand over the session to our resource person.
Yeah, thank you for the wonderful introduction. Am I audible?
Yes, ma'am.
So shall I continue the lecture?
Yes, ma'am, you can.
Yes, ma'am. Yes, ma'am.
Just a minute. I just share my screen. You can just update me whether you are able to see the presentation. Yeah. So very good afternoon, all of you. Sorry, a very good morning, all of you. Thank you for the introduction. So the topic for the FDP says smart grid. So here I have not directly gone into smart grid. So as introduced, I did my PhD in distributed generation and microgrids. So I would start with distributed generation and microgrids, and also nowadays people talk about nanogrids. Right? So we'll just see the basics of it because nowadays this has become a very, I can say, a very catchy area, or I can say it's very niche area, right? So we'll just get a glance through this. Then finally, I'll touch upon smart grids as well, because still many have a misconception that smart grids and microgrids are one and the same. but it's not so. That's why I have particularly added here as smart microgrids. So we'll just see what is the basic difference between a smart grid and a microgrid. Or in other words, I can say we'll just see when does a microgrid become smart. Right? So this is the content for the day. And finally, I'll be sharing a work which was done by my first research scholar. He has completed his PhD in 2019, and he did his postdoc for about 6 months in IIT Kanpur. And now he's an assistant professor, Dr. Suman, at IEEE Department of MNIT Allahabad. So that is purely a blend of what I can say smart as well micro. So I'll be presenting the results of this PhD work as well at the end. So this is how I have organized the lecture for today. And before going into the lecture, please, audience, you can always stop me if something you are not able to, clearly get it. So you can feel free to discuss anything. So this is what the topics to be covered for today's lecture. First, we'll see some introduction, and then we'll just touch upon architecture and modes of operation of microgrids. Then we'll look upon islanding issues, because if you look at these islanding issues, it deals with, say, I can list islanding issues as a protection issue, or I can use islanding as an operational issue at steady state. So it is very, very important, but I feel it is very less addressed in literature. So we'll just touch upon that. And interfacing of DGs make a lot of sense as far as microgrids and DGs, or I can say islanding everywhere is concerned. So because it's all about interfacing, how do you interface different types of DGs, right? So whether it is because of, through solar, so that you have inverters, or is it with rotating machines, so that you have induction machines or synchronous machines. So likewise, based on the interface, you'll have all the controls. And microsource controllers are not applicable for nanogrid or rooftop or single house. It makes a lot of sense when it is at a distribution system level or at a microgrid level. So we'll just have a glance on that. And finally, what is smartness in MG? That is, MG is microgrid. So what is the exact smartness here? When does a microgrid become smart? And this DC microgrids is something which is coming up gradually, because if you look at knowingly or unknowingly, we are using a lot of DC loads nowadays, which can be fed by DC source. But because we don't have such an option, we have the adapters, right? So if you look at all flat screens are coming to picture, all flat screen TVs, right, and desktops. And we have at every house, every individual nowadays has a laptop, a tab, and a mobile. So everywhere we have chargers where the adapters have this AC to DC conversion. So if we can have a DC line throughout the distribution systems, then you see the cost and the maintenance of this adapter can be completely removed out, or it can be removed off from the picture. So you can, like how we use AC, we can just plug it and then we'll be getting a DC supply. And electrical vehicles, including electrical vehicles, we can just go with direct usage. So gradually now this DC microgrids are also picking up because of such applications. Right? And finally, e-mobility, which is a typical example of a smart nanogrid, right? Because nowadays we go with solar-based battery charging units, fast chargers, right? And some look upon these electric vehicles as transportation of electricity, as well, because you can charge an electric vehicle at one point, and you just travel a short distance if possible, and then there you can connect it to the grid and take back that electricity if you are not going to travel any further. Similarly, when you want to return back that night, you can completely charge it, right? And then the next day morning you can travel back. So you will be carrying the electricity over here, so that you can again, if required, you can pump it back to the grid. So this gives rise to all E to B, right? G to V, V to G, V to H, and all that techniques are now coming up. That is vehicle to grid, grid to vehicle, right? So likewise, a lot of modifications and updates in the technology has come nowadays. And if you look at the fast chargers are the major concern, both commercially as well, based on the research as well. Right? So we'll just have an overview on that. So with this, we'll be finishing off the topic for today. Right? So normally I start with this slide because we have been taught with such diagrams, right? Maybe some 15 years or 20 years back when we were in second year or first year or third year in electrical engineering undergraduate studies, we were all taught with generation, transmission, and distribution. And when we were all students, we didn't think of these distributed generations, microgrids. Microgrids were all not at all known to us. But of course, it was there in existence. But we didn't know any concept of it. And to be frank, only when I started doing my MTech project, I came to know about this microgrids because in 2004, right? 2003 to 4. So till then, it was always not known much to the students community or the research scholars community. It was an R&D primitive stage, I can say. But it was there, it was in existence, but it didn't take up this shape. So we were not considering that more in undergraduate or postgraduate studies, except doing some projects or doing some PhD. So at that time, there was one candidate doing under my same guide when I was doing my MTech, and he was the first student in NIT Tiruchi who was doing PhD in distributed generation. So that was the case till 2004, right? That is 2004 in India, I would say, because NIT is one of the premier institutes, and even there, people didn't think of such mobility, or I can say such modern power systems, right? But now you see, we are approaching 2024, so hardly in 2 decades, right? In 2 decades, even school children are talking about distributed generation and microgrids, of course in a different language, right? So they don't talk about the same technology what we teach UG or postgraduate students, but they talk about solar panel integration, they talk about flexible PV panels nowadays, and then they do small projects with wind mill base, right? So the exact technology followed in windmills are being adopted by the school children, and they are doing small projects and they are showing some success, right? So the reach of this has become very great, I would say, just in 2 decades. And now if you talk about this, everybody will listen, and if you write a paper on this, everyone is ready to accept. But that was not the case even 20 years back. So this was the most comfortable system, right? Even till 2000, I would say, or the early 20th century, right? 21st century. So we generate somewhere based on the fossil fuels, right, or the natural resources like hydropower plants, nuclear power plants, or thermal power plants, and then we just cool it in the form of interconnected grids, right? And then we distribute it to long distances through very high and extra high voltage transmission systems. And then finally, we just distribute, right? Okay, I think it came out. Is my screen visible?
Yes, ma'am.
So that is why we call this system as a hierarchical power system, because there was a hierarchy. That is, first you have generation, and then you have transmission, and then you have distribution. So there was a hierarchy, both based on location as well, what to do first and what to do next. But now you see, there is the system which is shown below this red color dot. So what I mean to say, here you have a red color dotted lines, and below this you see wherever possible nowadays we have started to generate, right? So if I have a farm for a single house where I can lay, say, windmills, or I can have solar PV systems, I can just add it and I can enjoy the benefits, like I can get my bill reduced, right? And if I'm generating in excess, I can just pump them back into the grid and make money as well. Okay. So there are some different categories now, like domestic, commercial, right? And some are started to do this as a business. Like if you have a very large farms, right? And then they are investing on the solar panels, and then they get a commercial connection, and then they just lay the solar panels, and then they generate power, and then they export to the grid, and they make money with the help of net metering and all the services. Right? You just see now here there is no hierarchy. Wherever you have solar energy, you can generate, and wherever it's possible, you consume, and then excess you export. If you have a very good wind potential in a particular geographical location, just go by installing wind farms, and based on your financial status, if you are affordable with very huge capacity windmills, then you can install and you can just pump it into the grid. And if I'm right, in India we have not gone successful with rooftop windmills, but if you see particularly Germany and some western countries, they have small rooftop windmills, and like what we have with solar, they do have rooftop windmills, and then they have their own generation. Right? So wherever you want, you generate. Wherever it's possible, you connect it to the grid. If you want, you just consume. So this has completely eradicated the hierarchy, right, or a sequence, so that it has become a pooling, right? So if you have excess, give it to the other fellow. That has become something like a communism, right? So some sarcastically call it power communism. You just generate. If you have more, you give to someone else, right? Whereas if you want, and if your neighbor has more, you can just get from them. So that has been the trend, I can say, or the practice, right, nowadays in near past. So for the past 3-4 years, this open trading has come into picture, and it is yet to gear up in India, but we are expecting this to happen very soon. Something like if your neighbor has a very huge solar rooftop, you can even detach yourself from the electricity board, and then you can connect to that person, and you can just get your supply from him, and you can pay. So it is like an open trading, right? If people are interested in, say, share market trading, you'll be understanding that every company, they start with IPOs, right? So like LIC recently, they had opening for IPOs. So you have to apply. Initially, they'll give you in lots, right? So if you are lucky enough, you'll get. And then they'll float the company shares which were sold in IPOs with some basic cost for 1 unit. And then based on the market, based on the business, you will have ups and downs, and it will take some 1 year for the particular company to settle. But after that, it's highly based on the trend. So if you recently see IRCTC, after this lockdown, when the travel started, IRCTC shares have gone up like anything, right? But some 1 year back or 2 years back, it was not so. So it's all trend. Recently, infrastructure has come down slightly, but banking sectors are coming up. But 2 years back, banking sectors went down. So it happens in open trade as far as share market is concerned. Now, electric industry, or I can say the power industry, is going to face the same in recent future, right? So steps are being taken so that you will have more number of supply providers, and that is the height of automation which happens in demand side. But we are not at that level, we are just before that. So we have come to this non-hierarchical power systems, or I can say a pooling system, where whoever can generate at whatever level you can generate and pump into a common pooling system, and whoever wants it, they can buy. But still, the trade is being done by a single promoter or a
what I can say, appropriator, who is nothing but the government of India, right? So they have not opened up the whole complete open trade, right? But they have just pulled up, and still the government of India is the major, I can say, proprietor, right? Now, when you have utility grade, I have marked the 2 points as vulnerable points. Okay? What is this? Now, how to understand this vulnerable points? You see now, apart from this tie line, I can call this tie line. Now, this is the line which is connecting this part of the system. See, if I say this is one half and this is the other part of the system, you see this line is actually the interconnection of these two systems. Okay? And these two are initially considered to be a central utility power station with 600 megawatts each. Now, what is expected to happen if you look at the loads cannot stay constant. Okay? You will definitely have load fluctuations. But if you see the central utility generation capacity, it's fixed as constant, 600 and 600. Of course, we used to take care of the maximum demand and what can be the peak shooting up, all that will be considered, but at an extreme point of operation. If something happens and there is a very high imbalance, then what will happen, you see? Suppose I have an extreme peak increase of load here, this side, right? It may be due to a healthy increase in the load or maybe due to some voltage oscillation where it may lead to voltage collapse or just near unstable point or verge of instability. There will be a sinking point somewhere here. We don't know that, right? And this power station will be feeding it because there is a complete continuity in here. So this will be giving up the current. Now this will also load this tie line, and there is a vulnerable point where the thermal stability of this line may be overcome, or I can say it may cross its thermal stability. Okay, so what will happen is this tie line may lose its elasticity, and there is a chance for this line to get isolated when the current becomes overcurrent. Now, when this tie line gets removed out, you see what is the consequence? This is the only line which connects these two systems. So there can be a huge load shedding required in order to balance. Suppose if I have a 600 megawatt system here, and all of a sudden there is a sinking point or some heavy load has come into picture unexpectedly, right? Or unexpectedly all the loads have come into picture at the same time, which was not expected, right? Because normally if you look at the load curve, we don't have all the connected load coming into picture at all the time, right? So that is what the information shared with the load curve, when which load requires energy, right? So suppose if something has happened and by an accident or unexpectedly all the connected loads come into picture, or they are just switched on for some reason or by mistake, and if it goes to some 800 megawatt or so, then definitely this line cannot withstand its capacity. Okay? So such can happen, such rare occurrences can happen, which will always force this line to be opened. That is why these 2 points are considered as vulnerable points. Okay? Now, supposing you have a backup with solar or wind. Okay, then what we can do is, once this thermal stability going into its verge is identified, okay, once if this is identified, then what we can do is we can just bring the additional resources only during those critical points, and then we can help the system to become stable. Okay, so that is the major advantage of this distributed system, or I can say renewable system, whatever it is. Okay. Now, what are the challenges in today's conventional system? See, everything was going good for a long time. We were all happy with the existing systems. Right? Now, what has gone wrong? Why, or I can say, what are the conventional system challenges which are experienced nowadays? Right? If you look at the first one, lack of flexibility. See, a distribution system, this point makes its validity, but in transmission system, I cannot say, because we have gone into installation of more of compensators and controllers. So I won't say there is no flexibility, but in distribution systems, there are this lack of flexibility issues. Right? Similarly, coordination capabilities. See, because in distribution systems, most of the loads create unbalance. Right? Most of the loads create unbalance. So because of that, what would happen if you look at, right? What would happen if you look at, it is highly unpredictable, and so coordination, it doesn't mean that there is no coordination, but coordination is very difficult as far as today's conventional distribution systems are concerned. Next, proprietary architectures. See, we talk a lot about distributed generation, connecting the resources at different points, this, that. But still the proprietary architectures, like what I said, right? In India, still the single proprietor is nothing or none other than the government of India, right? Because there are a lot of issues when you go for open trade, and without a preparation, we cannot just like that make it possible, right? Because there can be some traffic issues. There should be an appropriate choice. Say, for example, one fine day, I have options. I can either buy my electricity from Government of India or from Reliance Power or Tata Power or my neighbor. Okay? Now, there should be a proper routing algorithm, right? There should be a proper routing algorithm. It says from this supply provider, you can get your supply for the next 2 hours or 3 hours. Then after that, the rate may change. So the dynamic pricing has to come into picture, and the customer should be given provision to choose among different supply providers based on economics as well as power quality. So that is not an easy joke, and the complete architecture needs to be analyzed. So it's not possible at a very short period of time. That is why still all these dynamic pricing and what else? Open trading, right, and this traffic control, all these are under research, and they are trying to make policies out of it. So without grid codes and policies which accommodate this open trading, if you open it up, then there will be a very big question mark for the power quality. That is why still we are following proprietary architecture. It is not our inability, or I can say it is not our what I can say, insufficient technology. It's not so. We are developing this, and in near future we'll be achieving that. So till then, we need a single proprietor, right? Which is obviously the government of India. But with that, there are some challenges. So you are always in a position to do business with the government. Right? You cannot fix your own rates, so you have to sell whatever you generate to the government, and then you have to buy for your usage. Right? It is not like you can first make use of what you want and then sell the excess. Actually, it is like that only, but it is not literally. You have to pump whatever you generate. Right? That is how grid-tied inverters have come into commercial usage. Whereas at the same time, you will have a parallel connection with the grid. Right? You want some electricity consumption, and whatever you want, you have to consume from the grid. So the net metering helps you to calculate what is the net consumption, and you have to pay. Of course, the selling price is different from the buying price, right? So these complications are still being challenges which avoid us or prevent us to go for a complete freedom of open trade exchange, right? So I won't say this is a disadvantage. That's why I'm using the terminology challenge. It's really a challenge. We are trying to overcome that. The next most important point is still the supply and demand have imbalances. Okay, still supply and demand are having imbalances. We are not achieving a zero difference supply demand unbalance. Okay, so because of this, what happens is this is a very big challenge, because from distribution level you cannot overcome this. Okay, because you know how to overcome this, but there are again limitations because of the above point. So we still have some supply demand imbalances or unbalances. Okay. The next is high deployment costs. See, all the above challenges can be overcome if you install a very high capacity renewable energy based distributed generation environments. But what is the major issue here is definitely the deployment cost is more. So as a single consumer or a single user, you cannot afford to this level. Right? So you have to think from business perspective, and that cannot be affordable, right, by many people. Though you are having a technically sound knowledge, but it's not possible. And if you look at, that's why government has introduced a lot of initiatives like say subsidies and all, right? So at least for your own house you can add something. In that, if you are not using electricity more, right? If the season changes, you are not using more of electricity, you have a lot of opportunities to sell, then at least you can make some money and help the government by supplying the power to the grid. But you cannot go for huge deployment because the costs are okay. The next is underutilization of DERs. That is also there, because if you look at the wind potential, in Trichy, Tanjore areas, the potential of wind energy is not very good, right? So either it goes to very high values that you cannot generate, or the availability is very, very less. But it's not so with solar. Okay, we have almost in a year, almost 9 months, we have a very good solar production. But still, you see how many of the domestic domestic users are using solar energy. It's very rare. In commercial buildings, in academic institutions like NIT, in DHL, we do have solar installations, but not many houses are going for it. Right? They are worried about a lot of issues, like they are worried about the recurring, expenditure that they have to do with the batteries, the maintenance, and the initial installation cost. Even though there are subsidies, people are not very well comfortable, right? Or I can say they are not very convincing towards it. They think this as an extra expenditure. They don't calculate it for the what I can say, the payback period knowledge is not being properly conveyed to many of the non-technical consumers. Right? So definitely I can say in Indian scenario, the DERs, that is distributed energy resources, are underutilized. Above all, some technologies are also not explored. Say for example, tidal energy. Okay? Tidal energy cannot be explored in all places. So there should be some, say Gulf of Kutch is a very good area where the natural, landscape should be in such a way to support your tidal energy. Similarly, offshore wind plants are also not very possible in every shores, right? But wherever it's possible, have we explored? That's another $1 million question. We have not done. And now if you look at, Power Grid has gone into a MOU signed already with Sri Lanka They are going to install a very good, huge offshore wind power generation plants on the shores of Sri Lanka, right? That is, they have identified the shortest route, and they are going to transmit the supply from there through underwater submarine HVDC transmission, and they are going to install some onshore, what I can say, onshore grid points on the shores of Tamil Nadu, right? And then from here they are planning to connect it to the grid. So the point of coupling will be on the shore of Tamil Nadu. From there they are planning to couple or connect to the grid. But actual generation happens in offshore wind plants on the shores of Sri Lanka, and the transportation of energy is going to happen through submarine HVDC transmission. And all the preliminary works have started. In India, Power Grid has taken up this project, right? And I'm not sure from Sri Lankan side who is taking up. If I am right, it's a 600 kV bipolar transmission system with submarine HVDC transmission. Okay. But you see, for installing or for commissioning this, they have taken more than, if I am right, all this started some 8 years back, right? But now only it has come to commissioning stage. So definitely underutilization of DERs are happening. Similarly, thermal energy as well. Underground thermal energy also is not being utilized to the maximum possible extent in India. Right? There are a lot of reasons for that. Let us not go into it, but there are challenges which are due to underutilization as well. So these are the major challenges which are happening in today's conventional systems, where even though we have a lot of renewable energy potential, these are the challenges which are being faced by the conventional systems till date, right? Fine. So now what is this distributed generation? Because we have challenges in the conventional systems, we have to try to find a solution for that. So one such solution is nothing but distributed generation. And why do you call it distributed generation? That's what is very, very important. But of course, all of you might be knowing the content of this slide. So it is generation applied at distribution level. And the capacity now it has gone up to some, say this shows up to 10 MW, right? But they are going more than that nowadays. And the generators may be either located at the site or at the isolated site. Anywhere, wherever possible, wherever suitable, you can push the generators. And the next important one is cogeneration. We have a cogeneration option in BHEL. So most of the industries, they are going for this because they have a lot of waste, right, in any form. And if they take some small steps towards recycling, they can clean it, right, and then they can burn. Instead of burning coal or instead of burning any other material for vaporizing the water, they just make use of this waste so that the waste disposal also is going to be efficient. At the same time, the heat can be reused. Then it is a very common mechanism. That is, once you get a lot of heat, you can just make the water boil and then convert it into steam. Then you can have a steam engine coupled with a 3-phase alternator and you can generate power. Right? So this cogeneration and other new technologies related to this are being incorporated as far as distributed generation is concerned. So I can say this becomes a part of distributed generation. And distributed generation is not dispatchable because what is dispatch? You would have studied about economic dispatch and unit commitment, scheduling and all that stuff long back. So here when it comes to economic dispatch, it shows the full control of the operator upon the power which is generated at any particular generator at any particular time. What is the basis for that? The basis is, see, if you have 4 or 5 generators, for what combination of generation will you get, right? For what combination of generation will you get the most economical fuel rate? But that is possible only if you add some fuel. It is not possible with renewable energy based because only whenever there is a solar energy availability, you can make use of it. when you want, you cannot extract solar energy or wind energy, whatever it is. So mostly distributed generators are going to be non-dispatchable category. Right? So what to do with that? What can be done in that case? If you look at, we have to utilize what whenever available. Right? So whenever solar is available more, give first priority to that so that you can safeguard or you can reduce the load upon the grid. Okay. Whereas whenever there is less availability, take more from the grid. Right? So that is what actually you can do to the maximum possible limit. Otherwise, you cannot do anything. It is going to be non-dispatchable. Okay. The next most glamorous topic I can say, or very attractive topic, is microgrids. Right? Everybody nowadays talk about microgrids. They say they are working in microgrids, and they are able to link whatever they work, wherever they work, to microgrid. Right? But what is this exactly? When can you call a system a microgrid? Right? If you look at here, it is basically an interconnection. Right? So small modular generation units, if they are simply present in a particular region, you cannot call it a microgrid. But if those units, right, are in a group and they are connected to the grid or not, that is optional. But there should be a combination of generation and load. Controllers may or may not be present, storage systems may or may not be present, but at least there should be some generators along with some loads, which can be very well called a microgrid. Right? Provided the voltage level should be at distribution level and the generation capacity should be at very few. Actually, this is a very old update. Actually, nowadays they go with few megawatts. This is just hardly 0.5 megawatt. But nowadays people prefer a few megawatts because wind turbines, single individual wind turbines, they are available nowadays with 8 megawatt. Right? So this can be upgraded to a few megawatts. Right? So that is the recent update. So, but definitely not in hundreds of megawatts. Right? So that is the difference. Definitely not in hundreds of megawatts, but it should be in the range of few megawatts, and the distribution level voltage should be there. If with all these requirements, if you have a connection or a combination of generators along with some loads, with or without storage, then you can call such a system as a microgrid. Okay, so this should be a proper. This is a most widely accepted definition, right? Because always we don't stick upon with IEEE standards and all that international standards, because we do have our own grid codes, right? So grid codes for India are now being established, right? So there should be some grid codes for Indian standards, because because I connect a generation system, I should not be creating a threat to the existing robust system. So there are some grid codes which have to be maintained. Say for example, frequency oscillations can be within this range. Harmonics can be within this range, that is total harmonic distortion. Likewise, there are some power quality based grid codes. And the momentary oscillations cannot violate this particular time period. Likewise, there are some set of grid codes which have to be considered. So subject to all that, if you have a group of interconnected small generation units along with some loads, with or without storage and controllers, then you can very well call it a microgrid. Right? So we got the point. So there are different words which people use in literature, right, which are most widely accepted. So they also call it as co-located power generation resources. That is, They are located nearby, right, with storage elements as well end-use loads. Some look upon it as a portion of a power system. Right? It can be a compartment of a power system, of a huge system, where some few DG units are present. And you see the third one, a cluster of loads and microsources. So it can be a cluster, it can be a group, or it can be a part of a big system, right? Or even it can be a self-contained power island. That is, it need not even be connected to the grid. Suppose I can generate some 150 kilowatt in a small place where it's a remote village, right? There may be some few houses, maybe 30-40 houses, where the complete load requirement, right, is going to be in few kilowatts. Then I can very well call that particular village itself as a micro. That is also possible. Okay. So not only the electrical boundaries, there are also some geographical boundaries which can be used. So this can also be looked upon as a power island. Okay. So this can also be called a power island if it is self-contained. Right. So now we just look at this pictorial representation. If you look at here, still I have the main group. Now you see the point of common coupling PCC is not going to be a mechanical switch. It's a bidirectional soft switch, right? So I have batteries, I have rooftop PV, I have wind farms or windmills, right? This can be rooftop or this can be in the form of wind farms. So if you travel south, then you can have a very beautiful site of wind farms. They don't have one or two windmills, they just have wind farms. Okay? And here you see we have flat screen household appliances and electronic gadgets where I can operate them with battery backup, or I can have a DC coupled subsystem. Right? So like how we have small distribution box in our house and we have different circuits, we can also have one particular circuit as a DC circuit. That is possible. Okay, so see, normally nowadays every house has an inverter, right? And in the inverter we have a bidirectional converter, right? So when you have power cuts, the battery is getting charged with one direction, whereas when you have power, right, the battery gets charged. That is when you don't have power supply from the grid, then it is being used. So that battery can even be made use of, right? And you can make one particular circuit. It's possible even nowadays, right? And if you have a rooftop solar, so you can just take the connection from the DC point. Before it gets converted to AC, you can just tap it at the DC level. And then you can just connect to one full circuit in your house where all your DC requirements can be met. Right? But as on date, what is the risk here is you have adapters. And if you don't have adapters, if you want a pure DC supply, then you can go about this. Right? So those days are not very long. We'll be getting that very soon. Right? So that is the prediction. Fine. So let us not go into that. Now here you see electric vehicles. Again, if you can purchase a fast charger unit, right? Then what you can do is you can just have your own solar panel on your rooftop, right? And then just install a fast charger. Then you can only buy one electric vehicle, right? Even on day, if your travel is going to be restricted inside the city, right? But if you want to travel a very long distance, right? Maybe taking outskirts of the city, then you need charging station. Whereas if you are located in a city, right, and you are going to shuttle from your house to the office daily, which is a few kilometers, then you can go with this setup. Right? In your house itself, you go for a solar panel, right, and then you'll be having a DC source available. Go for a fast charger, right? If possible, you go with direct DC, or if you have a fast charger as what commercial stations are using, You can just put a small inverter dedicated for electric EV chargers, and then you can give a plug point in your car shed, right? So that what happens, you see, your complete fuel cost comes to zero. But of course, EVs are costlier than your petrol diesel vehicles. But still, you need not spend what you spend for petrol or diesel. Only installation cost of the setup matters. And then the fuel cost is going to be completely free. Right? But one restriction is, if you want to take out of station, right? If you want to travel for more than 8 hours or 9 hours, then this charge cannot be retained. Right? You need a charging station in between. Otherwise, if you want to travel inside your city, you can do this. Now, you see the structure, right? Where is the hierarchy here? Hierarchy is a question mark, right? Whatever you want, you can connect wherever you want, provided you are subject to the rules. If not, what would happen is there are enough alarm systems and it's very easy to identify the customer who is the culprit. Then your connection with the electricity board will be cut off. Okay? Because they are worried about grid codes and the quality of the grid power. Right? If you are not going to obey, they are least bothered about you spoiling your own systems. Right? So what will happen at the worst case is they'll just detach your connectivity with the utility grid, so that whatever fluctuations you experience is going to be localized. That will not be traveling, right? Or I can say that will not be transported to the entire system. Because if it gets transported, then what happens? It's a big threat because we have a complete interconnected system. So this is the real structure of a microgrid, where you see we have storage systems, we have small generation units, we have loads, whatever you want to have. Obviously, there are some control units also incorporated, knowing you are. Right? So from all these discussions, this is the most unanimously accepted definition for microgrid. That is, it's a cluster of load and distributed source units, right, which are capable of operation in a connected mode or in an autonomous mode, or there can be also a ride-through between the above. What does it mean? Whenever you want to connect to the grid, you should have a provision to connect. Whenever you want to operate it in isolated mode, you should be in a position to connect. That is what the meaning for this, right? So if you look at here, you have a soft switch, right, which can behave as a power point of common coupling, that's PCC. So now if you are generating enough to supply the demand in this area, right, because you can forecast the demand or you can monitor the demand continuously. So if you are very confident that you have a very good knowledge on what is the requirement at this instant, and you know how much is possible to generate. Right? Suppose you have provisions for all that. Now, if you are generating exactly what is required as a demand, then you can voluntarily disconnect yourself from the grid. Whereas, on the other hand, if you are not sure when the demand may increase, right, then what you can do, you can get connected to the grid, but you can operate it as a backup. Right? So that is what being explained. You can either connect it in autonomous mode or you can connect it in connected mode, or there should be some provision for getting switching over, right? So that's what we call right through. So you can just switch over between the different modes which are, right? This is just a comparison, and this shows you the distributed grid management system. Okay, so let me speak of this. This is also just to show you how today's electric power systems work. Now, why have I shown this diagram? If you look at, we are very well familiar that distribution systems are mostly radial, right? We could have studied, we could have taught students that there are radial distribution systems where the R by X ratio is more, right, or X by R ratio is less. We have tapping facilities and all that. But now, what is happening? The radial systems are gradually getting transformed into weakly mesh or mesh systems, because the terminals are always vulnerable in a radial system, that we know, right? Because there will definitely be a falling potential, right? Or I can say there is always a threat for unstable population. But now, what we are trying to do with connection of all these DGs, we are trying to relocate, or we are trying to redirect the power by closing the terminal to the any suitable bus or any suitable terminals at the upstream. Okay, so what happens is we are preferring, right? We are preferring semi mesh, right, or weakly meshed or completely meshed. So that what we can do is, in a particular in-feed system, you will have a particular in-feed point, but this complete distribution system can be looked upon as a substation connection. And if you have a closed system, wherever possible you can generate, whoever it is possible they can generate, and you can just pump the power. Okay, so this is becoming the trend for today. That is, people are gradually transforming themselves, right, from radial distribution systems to mesh or weakly mesh or partly mesh, whatever you want to call it. Right? So that is why I particularly added this. Yeah. Now, as I told you, the controllers are incorporated without knowing this. So just as an example for that statement, I'm showing you this. You see here what is happening. This is a consumer, right? And I have a windmill or a wind turbine coupled with a generator, or this generator can be a diesel engine coupled with an AC generator as well. And I have a battery. I have solar. Now this is not possible, right, without appropriate PWM converters for the inversion, or a DC to DC converter, right, or a maximum power point tracking, or say a PLL technique, right, for synchronization. So all these are a part and parcel of regulation and conversion. You cannot deny it, right? We cannot deny it. But we don't know deliberately what's happening here, right? As a normal consuming person. Unless otherwise you dig into this, being a technical person, we don't have any provision to study this or to have any control of this. But that doesn't mean there is no control, right? So there are some controls incorporated in it, which is not known deliberately, but it happens, without which it's not possible to have this interconnection or the microgrid being operation. Right? So just to show that, I added this slide, because whenever you talk about integration of solar or whatever, right, small wind turbine or whatever it is, please don't come to a conclusion there are no controllers at the end user level. There are controllers. Right? They are not deliberately shown, or the control of such controllers are not deliberately given to your hands. That doesn't mean there is no such control at all. Right? So there are built-in controls, regulations, conversions, everything is happening. Right? Fine. So now there are different perspectives. One is from the utility side, the other is from the customer side. What is the approach from customer side? See, as an individual customer, if I'm not an electrical engineer, I don't think much, or I don't worry about all these interconnectivities, this, that, nothing. Right? See, from a consumer point of view, I want a very stable, reliable, rugged connectivity. That's all. Right? My electricity bill should not be high. That's all I'm worried about. Whether you generate from solar or wind or wherever possible, I just don't care. Right? I need a good quality power for what I pay every month or once in 2 months. So that is the perspective from a consumer side or a customer side. But from a utility point of view, you cannot just like that leave it off as a power So you do have a controlled cell of power system. That is the perspective of any control engineer from the grids. Okay, what are all these perspectives upon? It is nothing but about a microgrid. So from the utility point of view, the microgrid is looked upon as a controlled cell. Whereas from the customer point of view, there is no difference as on date, because as I told you, the government is the single proprietor, so we don't know who is selling wind power to the government. As on date, my house is connected to the grid and I am getting supply. I just don't care, or I don't know who is selling wind at what rate to the government. I just don't want that information, right? It is enough if I am clear about my electricity bill and how much I am paying every month or once in 2 months, whatever it is. That's all, right? My requirement ends up there. Provided the quality is good, I don't worry about this. Correct? So that is what the perspective means. Right? It is the headache of the utility to think about all this power quality, this, that, and all. I don't want, or I don't want even to worry about all that. I'll be worried only if you deny me power supply when I want it, right? I'm just returning back from my office. I just want to enjoy some air conditioner. And if you say no, then I'll be worried. Right? But otherwise, I'm not bothered about that. So, the perspective from the customer is like, whatever it is, whether it is a microgrid or it's a macrogrid, whatever it is, he or she looks upon the system as just power system. Right? So, this is a pictorial representation of a microgrid. If you have a single customer over here, right? If you have a rooftop solar, right, or a rooftop wind or whatever it is, then you can be called like this, where nowadays people call such customers as prosumers. Right? Because you produce and then you consume. So when you produce as well when you consume, you are called prosumers. Right? Produce and consume, so they are called prosumers. But you will always have provision to trade with the government. Right? There is no official third-party business entertained as far as power industry is concerned. But still, if you have a rooftop which is capable of generating on an average a considerable amount, then you can be called a prosumer, right? And you will be getting some benefit by making some business with the government about selling your generated solar energy, right? Whereas if I don't have any such provision, say this fellow, right? For these two fellows, they don't worry about whether the power supplied to them is from this DG, right, from this owner or from this owner. Right? It's none of their business, right? They are only worried about they need a continuous power supply. That's all. Right? They don't want to know, or they are not even interested, or it's not going to influence them in any means. Whether they get power supply from a third party or from the government, in what way it's going to affect them, so long as their quality of power supply is good. Right? So this is an example of a microgrid where you have a connection from the utility grid, which is a bulk supply connection. It can be either a sub-transmission level or a substation feeder or whatever it is. Right? Yeah. Now coming to architecture, I think microgrids I can finish off and then have a small 5 minutes. Right? So now coming to the architecture, what happens here is we have local microsource controllers. Then we should have a system optimizer, and then some distributed protection should also be there. Right? So what is this local microsource controller? We'll see. Right? And what is this system optimizer? We'll see. This protection, if you look at, it's a very huge area because there are a lot of issues related to distributed system protection. Right? It's not a very simple, straightforward area to explore. Okay? It is also going to be a huge area where we can explore a lot. But in general, the architecture of a microgrid, right? In general, the architecture of a microgrid deals with only these three areas. One is when you go with a large scale, relatively larger scale, then you have local microsource controllers. Okay. Whereas when you deal with some optimization, right, you need a dedicated optimizer. And obviously, when you connect distributed generators, you have to be worried about the protection issues. Okay. So you have to consider all these three categories if you have to deal with the architecture of a network. Right? So now, what are these microsources? There are huge number of microsources, right? So one is microturbines. You can have solar, right, photovoltaic, fuel cells. All these are almost used in India, right? Mostly they are used in India. But if you look at this microturbines, what is this microturbine? If you see, it's a small gas turbine where it runs at a very high speed. Okay. See, the speed will very easily be in the range of 150,000 RPM, right? Or it can go up to some 200,000 RPM, right? So you just imagine this rate at which the gas turbine rotates. Now comes the challenge. When you directly couple, right? When you directly couple this turbine, with an alternator, it's not possible to synchronize because the frequency will be at a very, very, very different range. Right? The frequency will be very, very high. Right? So it's not at all possible for you to synchronize it. So you have to go for, normally people go with AC to DC conversion and then DC to AC, where you can maintain 50 Hz supply with India as concerned. That is one major issue with microturbine, but now some lot of research is going on. And again, it's a German technology. Many German companies are coming forward for manufacturing this and installing this with appropriate controls. Otherwise, you can very easily use it because it's very compact and modular in structure, right? And you'll have a very high speed with a very small structure, so it's very, very safe, right? The others are familiar to you. Now, what is the requirement for this microsystem? It should respond to system changes, no matter what is the load or other source. Say, for example, in one point of point, if I have a inverter-based source and an inertial source. What is an inertial source? It's a rotating machine based. It can be a diesel engine coupled with a alternator, or it can be a wind turbine, or it can be a microturbine, whatever it is. If you have a combination of all this, right, then the microsource controller is very, very inevitable because it should respond to the system changes irrespective of the loads and the other sources. It should not be any one source or load should not be under the influence of any other source. So you need a decoupled, or I can say a very dedicated microsource controller when you have multiple sources connected, which is not a common scenario in individual customer. Whereas when you go for a large scale installation or deployment, then this is very, very essential. The other basic requirement is it should not worry about communication between microsources. Right? There should be individual dedicated control, or I can say communication with respect to each and every microsource controller. On the other hand, what can be the communication happening between microsources. Right? Whereas you should be very clear on from where the information goes to who. Right? Fine. The third and fourth point, you see, there is a regulation possible with power flow as well with voltages at the interfaces, because see, when you connect any other resource at the point of common coupling, this may have an issue with your voltage at the connecting points, right? On the other hand, if you have a connectivity with the substation feeder or a very main input feeder, right, then what would happen is there should be some control or check on the power flow on the feeders. Okay, so what is very important if you look at, right? What is very important if you look at, the regulation should be done, right? Whether it is going to be happening for voltage or power, that depends upon the way in which you connect. Otherwise, in general, you have to go about with some sort of regulation, right? And in some cases, it becomes mandatory or inbuilt, whereas in some cases, the control operator has to take care. Okay? And we'll look at this last point in islanding operation, because once you go into islanding operation, you should be capable of enhancing this rapid looping, because see, post islanding and during islanding, you will definitely have difference in the operating conditions. There will be oscillations, there will be some variations in the frequency and magnitude of voltage, but all this should not affect your load pickup capability, right? So there should be very rapid load picking on islanding operation. Now the next important component of your microgrid architecture is system optimizer. So as I told you, all important optimizations have to be controlled by this system optimizer, because you should have a control on the heat and electrical loads. You just minimize emissions. These are all most preferred, right? So most of the power system people will be very much working on optimization, right? Because it is a part and parcel of power system analysis. So here what is important, if you see, obviously you have to maximize the efficiency, minimize the losses and emissions. And the logic control, right? It should be purely of a logical control. In that, what is actually the optimization if you look at? The optimum logic choice, right? There can be too many logics for a particular island operation, but you should be very careful in choice of the logic, right? Which will give you a very optimal structure or optimal operating point or whatever. So you can fix your requirement, right? But where will this be installed practically if you look at the point of common coupling? There should be some control logic if you are going to install for a huge or a considerably big system. Okay, so recently BHEL has gone into a solar plant, okay, which is whose capability is in megawatts, right? And now they are planning for the next stage of operation, where they are planning for a solar thermal. Currently, they have installed a solar PV, right? And now they are planning for a solar thermal, right? With all concentrators, which focus the thermal, the heat energy, right? And then they will have a steam turbine, right? So the basic steam turbine will be used, where they circulate the water, right? And once the steam is available, then as I told you, you can go ahead with coupling a synchronous machine, right? A prime mover coupled with a synchronous machine, and then you can go with the conventional power generation. So they are planning for one such solar thermal power plant, and I heard all the initial procedures are done, and now they are planning for commissioning. Okay. So you'll be in need of lot of optimizations. The position, the heat, right? You cannot go for more heat as well as heat. It should be of optimal limit, right? And the steam flow rate control. Likewise, there are many gauges where the optimization is. So it is not just a laptop or a desktop where you run your optimization should be a very much real-time organization where you connect all the data and just go for a update once in very few milliseconds or microseconds or seconds, whatever it is, based on your importance, or I can say the delicacy of the operation. Right? So this becomes a very important part of your microgrid architecture. And finally, distributed protection. So your microgrid must respond to the faults. Right? So you need a protection unit, right, which actually should respond to all the faults. Either it can isolate your DG once the fault is identified, or it can isolate the complete microgrid when you have a fault, right? Or it can just go with isolating the fault. But whatever it is, the speed of operation expected should be very, very high. If not, what will happen if you look at your generator may get affected, right? Or sometimes what can happen is, say, picking up of the load on post-fault recovery will become a very big question mark, right? Or even I can say the power quality will be a very, very big issue, right? So the post-fault recovery will be very, very tedious. Fault can be recovered, right? The fault can be nullified or fault can be recovered. But post-fault recovery will become a very big question mark if you don't throw in some light or if you don't take some control on the distributed protection when you go with microgrids. Okay, fine. So these three are the major components of microgrid architecture. Now coming to modes of operation. As we have already seen, there are two major modes of operation. So one is autonomous mode and non-autonomous mode. And this is the user's choice. Right? So there are some issues which you have to consider. See, in autonomous, what does it mean? You are not connected to the grid. Right? So without grid support, you are going to supply power to your customers. So in this case, what will happen is you should take the sole responsibility of generation and demand balances. Right? Suppose your generation is more, you cannot dump it. Whereas if your generation is less, then also you cannot supply your full of the demand. So only if you are very confident that you can manage this generation and demand balance, then only it is possible for operating it in an autonomous mode. Otherwise, it's not possible. Right? Whereas in non-autonomous mode also, you can just physically connect to the grid. Right? But what you can do is, if it is possible to generate more, you can keep on generating so that your grid becomes a backup. Okay, the grid becomes a backup unit. So what will happen is, in this case, the connecting transformer will have a very good life because you are reducing the load upon that particular transformer. So normally transformers are those devices which are continuously in operation. Right? So when you connect through the transformer and when you are operating it at non-autonomous mode physically, but still you are generating as much as possible, then what happens is the life of the distribution substation transformer will have an improvement. Okay, so that is the major difference. Otherwise, always you have to take care of the other architecture-based issues which we have discussed. Okay, so let us quickly go through the basics of islanding and directly I'll go to the case study. Because, I think I have around 50 minutes more. So let me wind up in 40 minutes and we'll have a 10 minutes discussion. Okay, so now coming to this islanding, what is exactly islanding, right? Whether it is a blessing or a curse. So when I call something, some event as an islanding, I mean that disconnection of generators is called an islanding. But it is not so simple like what we think here. So this disconnection of generators can happen with or without load. At the same time, this can happen as an accident, or it can happen to avoid unintentional islanding also. Right? So if it happens without any intention, accidentally, right, then we call it unintentional, or we call it accidental. Right? Okay. Whereas if you voluntarily or consciously make islanding to happen, then I can call that as intentional. Okay. Now, what is the difference between the two? When it happens intentionally, it is in a controlled fashion. Okay. So sometimes people call it controlled islanding, right? So you will have full control on when the complete disconnection should happen, this, that, and what is the voltage, right? What is the frequency? So the complete monitoring will be there, right? Whereas when it happens accidentally, you cannot guarantee that there is a generation and load balance, or whether the grid codes are satisfied. So there is no guarantee for all that. So when it happens accidentally or intentionally, that decides whether it's a blessing or a curse. Okay. So if you effectively switch between this accidental and intentional islanding, then this will increase the local reliability of any particular system. Right? So that is the basic one-line definition of islanding. So when it happens accidentally, what you can do, if you look at, we cannot do anything, but you should have a proper islanding detection scheme. Right? So how fast you detect an island? Because accident is an accident. You cannot predict it, or I can say you cannot avoid it. Right? It happens when the system goes out of your control. But at least you can devise a mechanism which can identify the islanding at a very fast time period. Right? At a very fast time period, at a very short duration, if you can identify, then that is going to be a great help. Right? That is what is the basis for islanding detection schemes. Right? Whereas this intentional islanding is completely under your control. So what you can do is you can use this for reconfiguration, right? Or suppose you are generating on par with the load, then you can go for intentional islanding. You can just isolate the system whenever you want. So such systems you can operate, and in that case it becomes a blessing. Right? So that's what there are two categories. So the same thing which I told you. So intentionally what happens, you see, the isolator switch will be appropriately operated, and this helps in intentional island formation. And in this case, even after isolation, your generation should continue, right? So that you have to meet out the demand appropriately. Whereas in case of, after you undergo some intentional islanding, what happens, you see, you will have formation of control islands. Now the problem is restoration. So you should have a mechanism of restoration in your hand before you try for intentional. Right? Because reclosure again is not very simple. Right? Reclosure is not very simple. So you have to, you should be ready. You should be ready with a mechanism which helps you to reclose it at appropriate instance, or whenever it is not safe for the system to continue in island. You have to take a decision. So that risk, or I can say challenge, lies in your hands. But coming to accidental islands, you don't have any control on when or how it happens. It may be due to a mal-operation of a protecting device, or it can be due to a severe fault, right? Or it can be due to some loose connection, very simple reason, right? Or it could be due to some fluctuations where the protection unit operates. It just identifies the operation, the alterations or the oscillations, and comes to a conclusion that it's very vulnerable. So even though it knows very well it's not a fault, because of the extreme conditions of the operating parameters, it can isolate it. Or it can be a maloperation of an isolator, whatever may be the reason. So you see here the transients will be very prominent, and these transients are mostly dependent on pre-islanding operating conditions. What is this? See, before the islanding happens, if I am operating it with completely fully loaded system, or do I move with a 50% loading or lightly loading system? So that is going to be one major result, right, or a major influence which decides how severe the transients are. Right? The other one is, you see, type and location of the fault. The location, of course, how far it is from the heavy loads, right? What type of fault it is, whether it's going to be a very, what I can say, the three-phase short circuit fault, right? Or whether it is going to be just an oscillation. So the type and the location of the fault matters a lot. And the time detection, right? The time for the detection is also very, very important. And post-fault switching actions. So based on all this, the transients are going to be. And of course, by type of the DJs, because see, as far as inverters are concerned, right? As far as inverters are concerned, you don't have any inertial issues. Something like if you have a small rotating generator, then you have the moment of inertia which creates the rotation. But this rotation is going to be, you could have studied this in your power system, that is swing equation law and stuff. But that's not the case with inverters. Right? In inverters, what happens is it's completely the PWM based current control. So if you have some threads, right, the code says you have to isolate the DG. That's it. Right? Just isolate the DG for safety. So you will not find any transient oscillations as far as, say, inverter based DGs are concerned. So it becomes still more difficult for us to identify when this islanding happens, because there is no much indications, right? So that becomes a much more tedious job, or a very riskier job, to identify whether there is a islanding. Whereas if it is a rotating machine, right? If it is a rotating machine, like a synchronous machine or an induction machine, then it is going to be very easy for you to identify, right? Because automatically your voltage and the rotor angle or load angle keeps on oscillating, so it's very easy for you to check out whether you have got an island or not. Right? So the transients are the major issues as far as accidental islands are concerned. So from monitoring the transients, you can just come to a conclusion what I mean, when the remedial action should be taken care of. Okay. Similarly, this reconnection, right? You have undergone an accidental island, but you see the reconnection is always advisable only after complete restoration. You should have identified the problem, you should have removed off the reason behind islanding, and then you have to go for reconnection. But in that case, synchronization will be a very, very what I can say, a riskier job. Okay, fine. So these are the two broad categories of islands, and of course these are all the consequences you can guess, right? Even the worst case, it may lead to cascaded outages. That is obvious, right? That is obvious, because if any see, if any one line gets overloaded, and if that is creating an issue with the other line, then it's a cascaded issue, right? It's a cascaded issue. So what will happen is gradually, right? Gradually, this will create outage of many lines, which is called the blackout. Sorry, actually it's a brownout. Whereas if it goes for a complete outage, then I call it a blackout. Right? So this is a very, very worst case operation, but even you should be prepared for that. Right? You should even be prepared for that. Right? So So that is why this becomes very, very sensitive, I can say, or critical, I can say. Right? It's not very easy, and this transients and the dynamics stability are majorly the prominent issues which you have to consider. Okay. Fine. Now, this is an example for adaptable microgrid. See, as I told you, there are two options for the islands. One can be accidental, the other is intentional. Now, here you see all these red colors are isolators. Right? Now, geographically as well electrically, the isolating points or the I can say the locations are identified well in advance. So you see, now initially all are physically connected. Right? Now when any one microgrid or sub-microgrid undergoes some problem, it can be a fault or it can be an oscillation, right? To safeguard the other sub-microgrids, what you can do, just isolate that. Open this isolator, open this isolator. This will be isolated completely. Right? This will be completely isolated. Whereas the other sub-microgrids will be fine. Right? There won't be any issues in that. Or in other words, if 3 sub-microgrids are having problem and one is safe, to safeguard that particular microgrid, you can isolate these two or open these two isolators. Then you will be having the safe operation for this one particular microgrid. Okay, so it can happen on either way. Either you can remove a microgrid where there is a problem, right? Or you can protect a small portion of a microgrid which does not have problem. So maybe for safeguarding that particular one, you can just isolate that, and later on, once the main problem is resolved, you can just connect it back. Right? But you have to be very careful about the restoration activities. Okay, fine. So this is just a single line diagram. I have explained all this, so I'll skip off. So now this is advanced interfacing. So as I told you, these are the most available options. Right? So these are the available options. One is, you see, for micro turbines, wind, and all that stuff. We have to go about with rotating machines. Right? We have to go about with rotating machines. Whereas if you have inverters for fuel cells and for solar, then you can just go with battery backup and inverters. Right? So the interfacing becomes soft switching. Right? Whereas in the other cases, you have to go for some mechanical coupling, and synchronization becomes a matter. Right? Fine. So all the transients and all the dynamisms, all the issues are related to the interfacing machine. And when to connect this and when to isolate it is again a big issue. You cannot operate the islanding techniques. The same technique cannot be operated for inverters which are static and for the rotating machines, because the inertia will create a lot of issues. So you have to compute the inertia. So these are the different interfaces. And these are the power quality issues which arise if you don't care about these. Okay? I think I can switch over to the case study from here. Before going, as I'm limiting due to time constraint, I'll just show you the main scope for research and challenges. Because obviously many participants would be having an idea of doing PhD or already registered for PhD. So these are the design issues, right, which you have to focus, because there are a lot of problems available in this area, right? Please don't think that already the optimal sighting and sizing, have achieved its what I can say. It's all obsolete. So don't come to such philosophies, because as far as conceptual design issues are concerned, now people have started to incorporate energy management. Okay? Similarly, islanding can also have an issue or can be considered as a part and parcel of design issues. And you see the type of the networks, right? Whether it is AC or DC or embedded or it's radial or a reconfigured system, on what basis, on what criteria you reconfigure. So there are still lots and lots of issues where people are working. It has not become obsolete. Right? Then protection options. So protection is a very, very interesting area where there are a lot of unsolved problems, or I can say there are a lot of problems to address from design point of view as far as microgrid is concerned. Then comes communication, right? See now IoT is gaining up. What is this IoT? Internet is there for a long time, right? But a mutual communication within internet and any other device was limited, I would say. I cannot say it was not there. It was there, but the applications were very much limited. Now what has happened is all of a sudden people have started to use this communication wherever possible, right? Wherever possible, now people advise us to make use of this communication. And moreover, we are trying to make it bidirectional. If you simply store the data in internet, it becomes database management, right? Whereas if you are really going for a bidirectional communication, that is, you store data as well, you take some action, right? And there are bidirectional communication. The sensors give data to the what I can say, the cloud, and as well it takes information from the cloud. So whenever you have this bidirectional data flow, then the communication system becomes very, very important because it's internet-based communication. It's becoming a very wide area as well. It's becoming very rapid, right? So the next generation communication infrastructure is a very, very important area, right? So now we go with Wi-Fi based because wherever you need not have any wired connection. So likewise, some standardizations and some commercial protocols are yet to come as far as India is concerned. So you will have definitely a lot of scope in that area as well, right? We just have grid codes, but there are a lot of areas to explore as far as this standardization of the protocols are concerned, commercial protocols. Right? Still, we don't have a very commercial standard protocol for all this. Even for IoT, for interfacing of the DGs, we don't have a very established protocols. Right? So that is a very, very interesting area because you will have to do lots of survey and then incorporate the Indian scenario and come out with protocols. And in some cases, the protocols are available, but hardware to support the protocols are not available. So you can even dig out for problems in that. So in all this, these are the issues to be taken, which we have seen, right? There is generation type, interconnectivity, penetration level. What is penetration level? Suppose I have, say, 5 megawatt is the load demand. In that 5, how much I am going to supply from DGs? Say suppose 3 megawatt is being supplied from DG, then 3 by 5 is the penetration. The rest I will be getting it from the. So now people are trying for 100% penetration, and even though you have a physical connection, you can use it as a backup. Then voltage profile is very, very important. So here comes when you shift to mesh systems, then it's going to be very, very easier for improving the voltage profile. Right? And obviously, autonomous and non-autonomous systems have their own plus and minus. So now coming to integration requirements, again, there are issues. Now, you have network and device interfaces. That is the job done by most of the sensors. Right? Because nowadays we are working more on sensors. But you have already started to transform from measuring meters to sensor. And now the next level of improvement is the sensors should be very modular and they should be capable of self-tuning and getting connected to a wireless internet so that all these data can be updated, and this will help very much in network storage. Obviously, you'll have challenges. So these are all the technical challenges, right? So definitely you'll have relatively large imbalances because the requirement from the demand side is keeping on increasing, right? And as far as what I can say, the size of the DGs are concerned, if you increase the size, then you will encounter the other issues. So you cannot increase it, right? And whenever you deal with power electronic interfaces, you are playing with the power quality because there are chances for harmonics to get injected into the system. Right? And unbalanced operations are very common in distribution systems because the distribution systems are made for loads, so you cannot maintain a balanced operation. Right? So these and many other technical challenges are also there which have to be addressed very meticulously. So these are all known to you. Let me skip off all this. Right? And now I'll just go to because I'm restricting not to enter into protection because protection is a separate area, right? So I'm not entering into protection. Now just one or two slides on smart grid. Right? So what is smart? A system becomes smart when it is capable of deciding by itself or when it is capable of interacting with, say, man to machine or machine to man, something like that. Right? It is not mere automation. Smart is something like a decision making. When a system is capable of deciding by itself, then it can be called a smart system. So, smart, when a grid becomes smart, you can call it smart grid. So, you see, what are the smart grid components? New sensors, integrated communication systems, right? First, distributed power generation, smart meters, building automations, storage and automation of storage. Right? So wherever you have some automation which is capable of taking some decisions, I can say which is capable of operating by its own, then I can call it smart system. So a distributed generation or a microgrid need not be smart always. Okay. At the same time, your conventional distribution system can also be made smart. Something like demand side management is a very good example for smart systems. Okay. So a system to be smart need not incorporate distributed generation or right. So this is what you have to understand. Microgrid can be smart, but all smart grids need not be microgrids. Even the existing distribution system, the conventional systems can be made smart by incorporating the artificial intelligence or the decision making capacity. Right? So you see what are all called smart grids, wireless, security, right? Mobile communications, and the load control systems, right? Whenever all this happens automatically or with the updation or an automation, right? With the decision making capability, then I can call it a smart. Right? So I hope the full FDP topic is smart grid and future trends, but this is a very first lecture, so I have focused more on distributed generation and microgrids, and I hope I made it clear that smart grid is different from distributed generation and microgrids. So you see here, these are the barriers to smart grids. See, for example, I have a demand side management which decides when who can operate his own washing machine or dishwasher. This is totally against the culture of the customers. Right? See, I have made my own house. I have bought my own home appliance, and my mindset is like I will use it whenever I want. For that sake only I have spent this much, and for a sophisticated life, I am just spending this much for maintenance. But still, someone else, right, is telling me that I cannot use my air conditioner for 5 hours today, or I cannot use my washing machine now Why should I wait for someone else to instruct me when I can use my washing machine or dishwasher? This is what actually a part of cultural value, right? So even when these windmills were installed at earlier stages, many farmers were all totally against it because they were telling, see, this is a great threat to the birds, and see, they don't know such structures are too heavy, and then they will try to come closer, and they really got hurt. Right? So because of that, there were a lot of opposition, and they were saying that this noise is very irritating and they are not able to stay nearby. Right? So there are some certain, what I can say, certain cultural barriers as well. And you see the regulatory risk, as I told you, there are still no much developed levels of protocols. Right? So definitely regulatory risk is there. And high levels of uncertainty. We don't know when we can use our own washing machine and dishwasher. So this gives you a very high level of uncertainty because the main aim is to avoid peak demand to occur at inappropriate time. Right? So it is completely monitored continuously, and then whenever the peak demand is there, there is a warning for people to use the heavy goods. And initially, it will start with incentives that if you use in off-peak time, then you will have a reduction of rate of 1 unit of consumption and all that stuff. Then gradually, if you are okay with paying more and still utilizing, right? Then there will be a warning, and finally, there is a chance for curtailing energy also. Okay? So there is a burden of operating and maintaining with the solutions of this. And there are some risks from cybercrimes because someone else is capable of accessing your washing machine. Sitting some thousands or hundreds of kilometers apart, somebody is capable of accessing your house. Right? Someone else is capable of accessing what you are doing, which is done legally. It is not illegal. Right? So there are a lot of chances for this cybercrime. So this is what actually one important part of the barrier to the smart. Right? But because of that reason, we cannot avoid it. So these points help us to en route towards smart grids. So one is regulatory framework. We have to patiently wait, and we have to support, right, as power engineers towards regulatory framework and putting into place the standards. And you see, planning for large scale rollouts, right? So all these will take definitely some time, but there should be some cooperation from the researchers as well from the power engineers, right, in order to cooperate with utility, right, or the service provider, whoever it is, be it a private party or be it a government. That doesn't matter, but you have to play your role effectively, right? So that is what actually the takeaway that we as power engineers have to decide. Right? So this and all you can get from any information. And finally, this DC microgrids, as I told you, there is a chance for a DC common bus in your domestic distribution loads as well. Right? So these are all the options where you use DC. So you can just go with an adapter-free adapter-free appliances or gadgets in your future so that you can directly charge it with DC. And obviously, electric vehicles will skip off this cost analysis. This is what expected, right? So automatic decision making is going to come in near future. That is, the vehicles are monitored, the SOC of the battery is being measured, right? And then the decision making is done by the charging unit whether to charge this vehicle or not. Once the decision is done to charge, and then it should decide who is going to come next and what should be done, right? So it can be a, no man charging station, which is possible. It is not. It may look like a dream today, but this is going to be happening in your future. Because already in abroad countries, there are no employees in the petrol or diesel pumps, right? So you have to go and park your vehicle. You have to get down and you have to fill your tanks, right? And then you have to swipe your card and pay, or you can have prepaid cards, and then you can keep moving. Right? The same is going to be the case, but the interpol is very, very effective. You cannot cheat and you cannot run away, because you will be caught in the very next interpol camera. Right? So once such interpols are being made very, very effective, or the infrastructure for safety and tracking systems are once in place, then this is going to be possible indefinitely in your future. Right? And this is another slide which shows e-mobility fits well into wider strategy. Right? So here what happens, you see, the buildings are nowadays transforming into smart buildings. You have smart locking systems, you have alarm systems, right? And people are going for net zero buildings nowadays, and there are some competitions and certifications available. So everywhere it's going to be cloud-based. And even now the CCTV cameras are being connected with the mobile apps, so that you can watch your camera, right, even when you are traveling, but there it's not cloud, it's in the internet, so that wherever you have connectivity, right, you can just watch what's happening to your house even when you travel. So these are all some examples of the smart systems, right? And if you look at the cooking appliances, even many have become smart. You have programmable devices, right? The induction stoves are mostly programmable, right? They are coming up with timers nowadays. You can fix the timer and then you can make use of it. Automatically it will cut off, right? All your air conditioners have this timer options, right? So these are all left unnoticed, but these are all already available smart technologies which can be integrated very easily once the complete grid or the complete system becomes a smart demand side management based system. So in charging as well, you can have a schedule, right? So the charging schedule, charging plan, individual customer tariffs, all this can be well ahead planned and then fed in the data, so that you can have a charging schedule and plan, and there can be some prepaid cards. So automatically you can just, you nowadays have contactless cards, so you can just sit in your seat, come park your vehicle in a appropriate location, like what you do in fast tags, right? You don't need to get down. It's all no man verifications, right? So of course sometimes it doesn't work, but the main background of all this is nothing but your RFID is being tracked, right? And then the amount is already updated in that, so that with that help you can just deduct for each time you cross the toll gate, right? And such a system is definitely possible in your future, or charging your electric, right? So this may be a dream today, but definitely this is going to happen in your future once your infrastructure is being developed and some regulatory protocols are also in place. Right? So these are 4 technology-driven trends, and these are almost shaking the complete automotive industry, I can say, globally. So in your future, I think you could have been familiar with an advertisement by Volkswagen or Nissan, I'm not sure. There is completely unmanned vehicles are coming, right? You can just go and get down in your office, and then you can just give instructions so that your car will drive by itself and go to a parking lot. Because in most of the abroad companies, they do have their own parking lots, right, with the names, or in an office they have a parking lot allotted for a particular person in that particular company. So in India, still we have hospitals for doctors. You would have noticed this. They would have mentioned the name of the doctor, so only that person can park his or her car in there. Likewise, in a gated community, you can go, right? In gated communities, the house number will be written so that you have your own parking lot, right? So even in NIT quarters, we have this scheme, but we are manually parking. So now what happens is, when the vehicle is capable of driving by itself, then you just go get down at the doorsteps and then give instruction. The car will automatically move go and get it itself settled in its own slot. Right? So that has come in practice, right? And even unmanned bikes have come. That is motorcycles, right? Have come. So they have GPS, so they can travel by themselves. Now the next stage is autonomous driving. That is, one vehicle can communicate with the vehicle which is moving ahead or which is coming in the rear side, and it can calculate its distance between the two consecutive vehicles, and it will adjust with the feedback signal automatically. The speed will be adjusted so that it will automatically decide whether to overtake or not from the alignment. Right? So suppose you have two lanes. If you are traveling in a double lane, right? If you are traveling in a left lane and if another vehicle is traveling before you, right, ahead of you, then your car will automatically sense the next lane. If the next lane is free, right, then it will increase its speed and overtake the previous vehicle, and then it will get aligned in any one particular lane. But again, I repeat, for all this, the infrastructure developments and the interpoles are very, very important. Otherwise, we are in no way inferior to the foreign technologies. We have all technologies, we have people to work on this. Only thing is the practical implementation of the infrastructure is a huge hindrance because of various reasons. That also is not depriving of technology. But you see, our population is a very, very big issue, right? So safety, the economic status of the country and the people. Suppose if I install a very costly camera somewhere, I have to give safety to that camera itself, right? So in remote places, there are more chances for someone to just take away the camera, right? So there are a lot of social issues. These are all social issues and psychological issues, right? So it is not deprivation of technology, but practically when you want to implement in a country like India, where the population is very huge and there are many people who are below poverty line or lower middle class, right? It's not that easy to implement something. So that is actually the operational difficulty. Otherwise, I wouldn't say that we are inferior in technology to any other, right? So it's all in place. It's all under R&D and commissioning stage. But practically, when it comes, the number which is required is very huge, right? And our own population is going to be very, very huge. As well, we have our own cultural barriers, right? And our lifestyle. So all these are being under studies, and people are, the government as well the private sectors, their R&Ds are now doing a lot of research on this, and they are trying to make customized, because you could have seen some advertisements where when they sell automobiles, they say customized for Indian roads. Right? Some foreign companies, they sell their cars in the same name and in the same brand, but some cars, they just customize it for Indian roads. I think very costly segment cars like BMW and Audi, they have also launched Indian versions, right? Because long back, Ambassador alone was the Indian car, or I can say the car meant for Indian roads, but now it's not so, right? How, in a sense, they have made some modifications to adapt to the Indian roads and the Indian lifestyle, because we don't drive long at a very high speed daily, but that is very common in most of the foreign countries, right? So the lifestyle changes are there, and the reality comes into picture before you implement a bigger transformation. Right? So that is only where we are in this stage. Right? So these are the 4 technology-driven trends, which is going to shake the complete automobile industry, right? When we connect automation. So with this, I'll stop. Due to time constraint, I have not shown you a case study, right? But you can always check out my profile, and the papers are, listed in my, NIT website. So you can always go to that and then get a glance over it, so that you will get to know whatever I was talking about. Islanding detection is not out of imagination, or it's not a theoretical work. We have implemented it, right? So with that, you can get a very good idea. So going to time constraint, I have not gone into it. Yeah, somebody has hand raised. Mrs. Dhanalakshmi. So now you can ask your doubts. You can even type in the chat box, or you can unmute yourself and you can orally ask.
Any queries from the participants?
I think people are very hungry.
Thank you, ma'am. Thank you very much for spending your valuable time with us amidst your busy schedule. We got a clear explanation on microgrids, smart grids, smart connected energy management system, and basics of automotive industry. Thank you so much, ma'am.
Thank you so much for the patient listening. And I apologize for the initial bit delay of 10 minutes because we had a meeting. I was expecting it to be over, but I couldn't make it possible. So thank you for the patient listening. And you can even mail me if you have any requirement for interactions. Thank you so much. Shall I leave, Meena?
Yes, ma'am.
Thank you.
So participants, the next session will begin at 2 o'clock. We can have a break. After that, we can join for the next session. Thank you all.